I'm Rachel Goldman. I'm a faculty member in material science and engineering and in physics. And I am one of the co-organizers of this year's Saturday Morning Physics. I'm very happy to provide you this morning with a couple of announcements and then introduce our speaker for today. So this is the second to last Saturday Morning Physics in this series. And in addition to this Saturday Morning Physics, we also have on this coming Thursday, there is a public lecture given by the Weiser Center for Theoretical Physics, Are We Alone in the Universe? Paul Davies in the Rackham Amphitheater, Thursday at 7 p.m. I also want to announce that 2 weeks from today, we will have our last Saturday Morning Physics for this academic year. It will be given here at the same time, same place, and it will feature a few graduate students telling us about the exciting things going on in their research. So now for the event we are here for today, I am pleased to introduce our colleague, Professor Abdon Pena-Francesch. I practiced.
Pretty good.
Professor Abdon, we'll just leave it at that, was born in Spain and spent his childhood in a small town, which he'll tell you about. This town is famous for wine production. And he received his bachelor's and master's degrees in mechanical and chemical engineering in Barcelona. And then he joined later the Penn State University as a PhD student. After his PhD at Penn State, he went to the Max Planck Institute in Stuttgart for a postdoc, and we happened to interview him right before the pandemic started. And we convinced him to promise us he would come as soon as the pandemic lifted for a little while, and he showed up in 2021. He's been very successful in his teaching and research, and I want to tell you a little bit about some of that. I can't name all of these awards, but of particular interest is an award from the Materials Research Society, Sustainability in Action Award, and this is for a course he created on sustainable materials design. And that course also helped us to land a new Materials Research Science and Engineering Center at the University of Michigan that includes faculty and students from physics, chemistry, material science, and mechanical engineering. In addition, Professor Abdon has received a number of awards for his research and to fund his research. Most notably, he recently won the Air Force Office of Scientific Research Young Investigator Award. In addition to his science, and I'll tell you when we have department open houses for prospective majors, basically everybody else's stations are really, all the students flock to Abdon's station, and you'll see why. So he's going to tell us today about Bioinspired Microrobotics, lessons from nature.
Thank you. Thank you, Rachel. Thank you very much. Yeah, it's great. So we're together with Rachel in the MERSEC, so it's great to work with her, but also thank you very much for the invitation in here. Okay. It should be on, but I think it will help if I actually talk to the microphone. I think that will be helpful. So thank you very much for coming. Very excited to see some familiar faces, some new faces, but also some very young faces here. So we have a lot of young scientists and engineers. So thank you for coming on a Saturday morning, right? We're gonna have some demonstration here for some of the work that we do, where we would love to have some help from you. So we'll be looking for volunteers in a few minutes. So first of all, Rachel did a great introduction, but I wanted to talk to you first about where I come from, a bit of my journey to here. So I was born in Spain. How many of you have been to Spain? Oh wow, a lot. Good. Those of you who haven't, you're missing out. It's a beautiful place. I'm very biased, right? But particularly you should visit the northeast, right? It's the Catalonia region. So I'm close to Barcelona, which is very famous for its soccer team and the beaches. But I'm from this little town in the mountains called Capçanes, right? So it's very, very little. We have 134 inhabitants, and we can count it exactly because we all know each other. And that's where I grew up, right? So that's me before science gave me white hair, right? So in this town, as Rachel was saying, is very famous for the production of wine, which is kind of what's keeping the whole region alive, right? But the town is very small. You can see we have great amenities. This is our train station, right? We have one train in the morning, one in the evening. If you miss it, see you tomorrow, right? We have great sports facilities as well, right? And we have one bar in town, right? Which is called the La Casal, which is kind of where everybody flocks. And my parents' house is right next to it. So we have prime real estate in the small village, right? So it's a beautiful town. If you happen to go to Spain, especially if you like wine, I recommend you visiting the region. And after I spent my childhood there, then I went to Barcelona for my bachelor's, and as Rachel mentioned, then I went to Penn State for my PhD, and then I went to Germany, to the Max Planck Institute in Stuttgart, where I started working and getting more interested in robotics, right? So I kind of combined all the previous work that I've been doing in materials, especially in biological materials, with robotics, and this is kind of what we're doing in here, in the material science and engineering department. So a lot of the things that we do have to do with understanding how nature creates some very interesting materials with unique properties that typically surpass what we see in engineering materials, right? And how can we adapt and apply those lessons, right, or the underlying physics and chemistry to synthetic materials to enable new capabilities in robotics, right? So this is our research group. We're very happy that we have many of them in here. They're gonna help me today. So we have Yushen, Caroline, Lakshman, Zain, and Chuchi that are gonna help me with some of these demonstrations throughout the day. And this is us, basically. So with this, I wanted to start talking about, these bio-inspired microrobots, right? But I wanted to first start with a question, what is a robot? See if you can help him with this, right? Can anybody give me an example or a definition? Yeah, please.
A robot is a piece of machinery that does either a job or a favor.
That is very good. Like, remarkably good. Yeah. This is actually what the Encyclopedia Britannica says. So you hit it the nail on the, you said, is that the nail on the head, right? Yeah? Can anybody give me examples of robots? Yeah, please.
An AI?
I'm sorry?
A computer?
A computer. Maybe, right? I think a computer is typically part of a robot, right? But it's definitely a very important part, right?
A Microwave?
A microwave. Kinda, yeah.
A camera.
A camera. These are. I think camera will be a part of a robot, right? So I think the formal definition of robot, right, whether it's from the encyclopedia, but also I think the NSF gives a more formal definition, right? Or they call it an an intelligence embodied in an engineered construct that can do several things, right? For example, can process information, which that's where the computer becomes important, make decisions, but also it has to sense, move, or somewhat interact with its environment, right? And especially it has to do some work. It has to do some mechanical work that we can use for aiding us in our daily lives, right? And but these definitions are, this is pretty vague definition, right? But it's something that is so new that most of our references for these robots come from sci-fi, right? And from movies. And this kind of can tell you a bit, these movies can tell you a bit about my age, right? The Terminator, RoboCop, one of my favorites, part man, part machine, all cop, right? But you know, these things are becoming closer to reality, right? And as you say, you mentioned a microwave, cameras, right? They're appliances that can help us in our daily lives, but we see this growing very fast, right? And we see a lot of these robots coming into manufacturing, into industries. We have here an example of a robotic arm or like bipedal humanoid robots that are real. And if you guys happen to go to the robotics building in the North Campus, they have many of these ready for you to interact with. So I will strongly recommend you to visit them. But despite all these, and I have here some more examples, right? On some recent robots, I have here the same example. This is the Atlas humanoid robot from Boston Dynamics. But we see that this technology is growing like crazy, very, very fast, right? From across scales. From humanoid robots to insect scale robots that can fly. Robots that can pour you a beer, which is with a perfect head. But despite all of these advances, right, we're still quite far away from replicating the behavior that we see in nature, right, and the kind of motions and the kind of agility that we see in people, right. I'm not saying that I can do all of this, right. But, if I train enough, I should be able to do some of it, right? These are things that, things like walking up the stairs, opening a door, right? Interacting with our environment, that for us come as second nature. It's very difficult for robots to perform, right? And particularly as we scale down, right, you can see how this is a white blood cell. You can see how they're able to perform all these crazy motions and how they're chasing a bacteria here, right? So they're showing a very sophisticated degree of intelligence and motion that we cannot replicate with synthetic systems. So we think we're very smart, not so much, right? But we have to start somewhere, right? And a lot of where these limitations of current robots come from is on, as I was mentioning, how they can interact with their environment, right? So in robotics, typically, you talk about two types of environments. Structured environment is something that has been already laid out, right? And this is where most robots that we see today operate in, right? Things like, for example, in an assembly line, right? Each of these robots have been programmed for a specific task in a specific control environment that doesn't change to perform this task many times, right? And they're great at it, right? That's why we see them a lot in assembly lines and across many industries. But the real world is not so much like that, right? So what we call unstructured environments, which is environments where unpredictable things can happen, right? Things like uneven terrain, there's obstacles, right? And I like to show this video. This is from the Arbor Robotics Challenge. And I have to say, to be completely fair, I like this video because it's funny, and it exemplifies how things that are simple for us are hard to do with the robots, right? But note that this video is it's a bit old, right? So, and robots are a bit like, they're like dogs, right? Like 1 human year is 7 robot years because they advance so fast, right? So there's a lot of progress that has been done to fix this issue already, right? But I think this is a clear example on some of the intrinsic limitations of this type of robots. But of course, this is interacting with a static environment. When you throw people in the mix, things get very complicated, right? Because we are very unpredictable, right? I don't know if any of you have pets. They don't like Roombas, right? So that's just a quick example. It's very difficult to program a robot to deal with this, right? So that's why operating in unstructured environments is very complicated. But this is a very active area of research. A lot of the things, for example, this again, that humanoid robot, where one of the guys from Boston Dynamics is messing with the box that's trying to catch, right? So, and this is a Franca Amica robot. This is from Sami Hadarin from Technical University of Munich. You can see how they're implementing new strategies and new mechanisms for safety, especially, right? If you're going to interact with a human, we're concerned about not getting hurt, right? And this is what's opening a lot of possibilities for collaborating with and interacting with these robots. But still, there are many challenges, right? Because we're not quite there yet. First of all, and this is kind of what we are focusing a lot of our research, is on solving some of the materials and design for these robot systems. For example, one of the big problems is how you can design robots that can work across different length scales, right? I don't know if you've seen this movie, Fantastic Voyage. It's a sci-fi classic, right? Awesome. It has a bit of funky special effects that didn't age great, but it's a great movie, right? They have, I think it's very important person has a brain tumor and they cannot access it, right? So they put a bunch of doctors in a submarine and they shrink the submarine to have access in there, right? It's kind of like the same thing as the Ant-Man. I think it's more of an updated reference, right? That they can shrink. Unfortunately, things don't work like that in the real world. We don't have shrinking rate technology yet, at least, right? So if we try to miniaturize these robots, at some point we run out of space, right? We cannot shrink actuators, batteries beyond their physical limitations, right? So we need to come up with new strategies, new ways to power and to control these things. Also, because we're limited in space, right? We need these robots to be able to perform many different functions within very few components, right? So things like robots that can adapt to and shape change to perform multiple different functions simultaneously are very interesting and can open up many opportunities for the new design of robots. And of course, if it has to interact with its environment, it has to be safe, whether it's interacting with nature and the environment, for robotics for farming, for example, they shouldn't be polluting. But especially, as you can imagine, these robots have a tremendous potential for medicine, for minimal invasive surgery, for therapy, etc. Right? So these things have to be safe. They have to be biocompatible. If it's a robot that can navigate in your body, it should degrade, so they don't have to retrieve it after. Right? So there's many challenges in the road to achieving that biology-like performance. Right? And a lot of the focus on robotics, traditionally robotics has had a main focus on the controls, right? And from electrical engineering, from computer science, but the hardware is also important, right? And I like to bring this comic strip with this scientist that created a robot that can play piano, but they gave him mitten hands, right? So I think it's a great example of how both the mind of the body, the mind of the robot and the body have to work together, and both of these things have to be considered in the design of these robots, right? Because we need a body, a hardware that has to be able to perform these functions, right? So, and this is the main area that we work in our lab, because I think you can see here there's a lot of opportunities from non-traditional roboticists, right? From chemistry, physics, material science, right? All kinds of engineering to bring solutions to this thing, right? And this is where our bioinspiration comes from, right? So we look at different interesting species in nature and trying to learn different strategies for motion, for control, from grasping. And we're trying to adapt all of these different things into the next generation of robotics. So what we're going to do is, oh yeah, I forgot I had this. And yeah, some of the things that we do: sensors, injectable microrobots, actuators, etc. But what we're very interested in is, of course, things at larger scale are kind of established, right? Because you don't have that much limitation in space. But we're very interested in miniaturizing these devices so we can use them inside our bodies for healthcare applications. So we're going to see today 3 examples of different bioinspired microrobots, more in the millimeter and micron scale, that are more on this region. And you'll see why things are a bit more complicated. Okay? We're doing good so far? All right, great. Thank you. So first I wanted to start talking about motors. Can anybody give me an example of a motor? So I cannot see. Oh.
Example or definition?
Both. That will be great.
A motor is something that powers a type of any robot that it can make it move, and an example is like a car motor.
Perfect. Well, car motors, I was going to say what type of engine they have, but they have 2, right? So typically, this is a beautiful definition. You can see, what did I put in here? Convert one form of energy into mechanical energy or motion, right? So this is perfect. It's 2 out of 2, so you're doing great. Thank you. Typically, we see motors at larger scale, right? Typically, the most common motors that we see today are combustion engines and electrical engines, right? And we see this in robots and in our cars, for example. As I was saying, this is very difficult to miniaturize because it has many moving parts, right? But the microrobotics community has come up with many different ways to power things at the micro scale, right? We're going to see some example using magnetic fields, using acoustic manipulation. But we're very interested in using chemistry, in using chemical propulsion, because this is what we see in nature a lot, right? From things all the way from microorganisms, for example, a spermatozoa or bacteria that have some flagella that can beat and move through fluid, or ourselves, right? We run on chemical energy, right? But also some insects that have a very unique, and we're going to touch on this in the next slide, have a very unique ways of locomotion. So this particular family of insects, Microvelia and Mesovelia, they're like cousins of the water strider, right? They can walk on water. But what's unique about these guys is that when they're threatened by a predator, they secrete this surfactant from their butts, and they sink it in water, and they're just propelled like a rocket, right? Is it gross? Yes. Is it cool? Hell yes. With this, they double their walking speed, right? So they go very fast, and they use it as like very fast bursts to escape these predators, right? And the reason for this is because they have this surfactant. They generate what's called Marangoni flow or Marangoni propulsion, they are locally decreasing the surface tension. And just this imbalance of surface tension with the water, it generates these flows that can really propel them, right? And we're going to do one quick experiment here to show this. So maybe we can, perfect, thank you. But we might need a volunteer for this. Yeah, please. Yeah, thank you. So this is Chuchi, by the way, so she's going to help you with this. So I got in trouble this morning from stealing pepper from my kitchen for my partner.
So you can use your hand to touch this.
I think it's okay. I think it's going to be better for this. So what we're going to do is we're going to put some pepper in here, right? And you'll see, right? Can we see this thing? Yeah, so you see there's a bunch of pepper in here, right? So what we're going to try to do, can you touch the surface real quick? With your finger, yeah, just like tap it real quick, yeah. Oop. Nothing happened, right? They're still in there. But now we're going to put some dish soap, right? On your finger. Can you put it like this? Okay, just a little bit. So soap, whoop, that's a lot actually. It's okay. Clean hands, huh? So can you do the same, just like a gentle tap on the surface? Wow, so everything got pushed away, right? Thank you very much. Maybe we can, yeah, perfect. Thank you, Monica. So what, oh, we got some. Thanks. Actually for me, I got soap all over. Thanks. Thank you. What's your name, buddy?
Tommy.
Tommy. Nice to meet you. You did great. Thank you. Let's give an applause to Tommy. Thank you, Gigi. So maybe we can switch? Yeah, awesome, thanks. So what happened there, right? Just that little droplet of soap reduced the surface tension and pushed all the little pepper away, right? But you can see this is very, very short-lived, right? This is only one burst, and so it's not very that useful. So we're trying to come up with new ways on how we can leverage these surface tension forces to actually power things, right? And for this, we developed this material that comes from squids, right? And I promise you it makes sense. It seems unrelated, but squids, I don't have time to tell you the full story today, but have a very interesting material in their suction cups, right? So you can see here, they have these creepy teeth inside their suction cups that they use to catch their prey, right? So these teeth are made from a structural protein, very similar to spider silk, very strong, but it has very interesting properties underwater, right? And one of these is that it has this dynamic porosity, right? So what we can do with this is, I'm going to go very quickly through this. Just I'm putting this in case you're interested. I can go over later in the questions. But we looked at the different chemical fuels, right? We're going to use here this HFIP, hexafluoroisopropanol. It's like a fluorinated low surface tension alcohol. And we're using this squid protein to entrap the fuel and release it very, very, very slowly, right? So what happens with this is you can see in here, oh, actually, I don't want to do spoilers. Yeah, maybe. So Chuchi, maybe you can show us what happens when we have some of this protein with the fuel entrap and we can put it on water.
Yeah, sure. I hope it's clear to see. We have a dot over here.
Yeah. Wow, so things can move pretty fast, huh? And now it's doing weird things because it's a bit bent, right? But I can show you in the video next there. Maybe we can add a couple more, yeah. Thank you. So you can see in here how fast this goes, right? So this is the same squid protein with the fuel and go crazy fast, right? You can see in here that when we use we use the same fuel as the swimming media, because there is no difference of surface tension, then you have no force, because you don't have any gradients and you have no Marangoni flow in there, right? And while other materials and other like porous materials, it still works, but it dies out very fast, right? You can see how these guys are pretty crazy, go pretty crazy, right? But what is very cool about this is that you've seen some example on these protein films, but we can apply it as a coating. And this was very interesting because then we can use it literally as a paint and power inanimated things, right? And for this, we're going to need another volunteer. Yeah, please. I think she was first. What's your name?
Ethan.
Ethan. He was first, but maybe you can go next. We have plenty of things. Come on, here real quick. So we have in here some, yeah, maybe we can grab it with this. Yeah, we have a bunch of different particles. Can you, wait. Maybe we can get some of this. So maybe you can grab it like this, and you can throw it in the pool. And you'll see that we can paint this thing, and we can have like this. Oh, that one is drunk. Yeah, I think it's partially submerged, yeah, but it's okay. But you see how it moves, right? Control is a different issue that we'll talk in a second, right? But maybe, do you want to throw another one in there?
There's M.
And maybe we can. Oh. So we can use this. Oh, it's stuck. Maybe you can. Yeah, perfect. Right. Exactly. Thank you. Awesome. Thank you very much, Ethan. Can you give an applause? Thank you. So we can use these Marangoni flows to move particles around, right? And we did this thing with 3D printed little version of the same bug, right? And you can see how we can kind of reproduce the same. Oh, I think the video got stuck. The same locomotion mechanism that they have, right? And we can use this for navigation through channels, and we can do this thing. Maybe we can skip the channel, yeah. Right? Yeah, and we'll do. Maybe you can get the gear ready.
Oh yeah.
Yeah, awesome. Thank you. So you can use it to navigate through channels, right? But this is pretty scalable, right? You can use it to any kind of materials that we have. And we got like this. We bought these like toy boats in our lab, and we made them race, right? As a function, you can literally, when you go to the river in summer, you can get your kayak, apply this paint, right? And it's too heavy for these kind of things, right? It works at small scales, right? But imagine you could paint it, just throw it in the river, and just enjoy, right? So that's what we're trying to do. And what's exciting about this is that we can use it to design all kinds of different mechanisms, right? So we had a little like shark that's swimming around. But also we can use it to power different mechanisms. We have here an example of a torque multiplier and a torque reducer mechanism. We can use it to power a gear train. And I think Chuchi has another example in here, maybe. Thank you. So wait a second, because it's not ready yet. Okay, yes, there you go. So hopefully it works. Yes, thank you. Thank you. So you can see in this case, what we did is we just apply this protein on different sections of the gear teeth in this case, so we can have this rotation, right? Thank you, Chichi. And here's another example, right, on how we can do like more complicated mechanisms. This is a gear train where we had some like a clutch system where we can design some other responsive materials to engage and disengage with the gear train. But what is very exciting about this is that because this is model and we can apply it as a coating to any kind of material, we can combine this thing with other microrobotic established technology, right? And this is where we are with this. These are some examples where we can use. In this case, on the left, this is a composite where we add some magnetic nanoparticles to the protein. And in here, we just stuck the motor to another magnetic microrobot as a backpack, right? And what's cool about this is that we can use these proteins for chemical propulsion and decouple it from control. And we can use magnetic fields for steering, right? Basically, we use our hands for steering and our foot for gas, right? So this is a similar approach. You can see in here that when there's no fuel, They rotate, but they don't go, right? And this is great because it gives you full control over the trajectories and the motions of the microrobot, right? So all of this from this little silly guy, right? So we're very excited about the possibilities of this propulsion mechanism because it's untethered, it's autonomous, it lasts for a long time, and it's biocompatible, right? So we're very excited about the possibilities that this has for microrobots for drug delivery and targeted therapy. Okay? Any questions so far? Okay. Awesome. Oh, there's one in there.
Here's a
I cannot
question.
see.
Hi. Yeah, this is really, really interesting. I'm kind of curious about, so what exactly is happening with this motor paint? Is it doing like a chemical reaction with the water, or is it like, and does it like change the water properties to a point where you can't use it after you've used it a lot in a certain region?
That's a very good question, yeah, which I didn't put all the details in here. There is no chemical reaction. What happens in here is just the fuse is diffusing in the water, right? What's unique about this protein is that it has a dynamic porosity, right? So as we fabricate these materials, it has an amorphous nanostructure, right? Because this fuel is preventing hydrogen bonding inside, so it's blocking beta sheet formation. These beta sheets are like nanocrystals that stabilize these proteins. As you put it in water, the fuel is leaching out, but when it's replaced by water, it closes the porosity by forming these beta sheets. So you have like a self-regulating mechanism. But there's no reaction. What is cool about this is that because this solvent is volatile, it evaporates, right? So you never saturate the water, right? So eventually things will die out when you run out of fuel or when you saturate your solution. So you don't have this difference of surface tension. But that's why we chose this system, because of these properties of both the fuel, the motor, and the synergies between the two. But yeah, that's a very good question. Yeah, thank you. Okay, so if not, we'll move to the next case. Is that okay? All right, awesome. So another species, another source of inspiration are inchworms, which they have a very cute way of crawling, right? And for this, to show some example, maybe you guys can help us. So we have a good model in here, which is worm gummies. So maybe I'll keep one for myself. Wait, can you guys grab one for me? Right? Yeah. Okay. So if you want some, yeah. So maybe you guys can go each on one. Perfect. Thank you. So and maybe yeah. Perfect. Thank you. So you can see how the inchworm, right? So it has this. Can we see up in here, right? It has this mechanism where it bends its body, pushes from the back, and then releases and relaxes, right? And keeps doing this kind of thing, this kind of motion, in either way, right? So this is something that has inspired a lot of dance moves, first of all, right? But also, it's a very cool way of moving, right? Because you are transforming here one-D motion, right, into effective locomotion in there, right? So I'll save it for later. So how can we adapt this thing to robotics? Like, well, we need to come up with a material and a way to bend it in these ways, right? Ideally remotely, so we can actually reproduce this motion. And for this, we're using magnetic fields, right? And I'm going to have just a couple of equations in here. And I think we have here the Zen. We have the magnet somewhere. Should be over here. Then, all right, yeah. So typically magnets, right, have, awesome. and I can put it in here. In here, this should be, so this little screen is going to show us the field lines of this magnet, right? So we can see how, well, kind of more or less. We can see, maybe here we'll see it more clear on this example, right? Or maybe put it under it. Yeah, I think that might be better. Okay, that's stronger, yeah. So you can see how you have these different lines that come from one pole of the magnet to the other, right? And typically, these are used to generate forces, right? Magnetic forces depend on the magnetization, the mass of your object, but also depend on the gradient of the fields. That means that things are attracted to the regions where you have more of these lines, right? And you get very large forces, but you need to pretty much, stick the magnet into its face. You need to be very, very close, right? So it doesn't scale that well with distance, right? But on the other hand, you have magnetic torque, right? That depends not only on the magnetization and the field intensity, but also on how they are aligned, right? And this is pretty much how a compass works, right? When you have a compass, you don't feel it, just pulled to the poles of the planet, right? But you can see how the needle aligns with the field, right? And there's several ways that you can use to, let me see if I can do it like this, to generate, there you are, to generate homogeneous fields, right? And you can have, rather than having regions with a lot of flux, you can have in here regions where you have homogeneous fields instead, right? So we can use this to design materials that can respond in different ways to these fields. And maybe we can get ready for the other demonstrations. So Zane here, right, works on developing different materials that can respond differently to magnetic fields, right? And what we're doing in here, right, is we're introducing to these polymers, these like soft elastic films, we're putting some nanoparticles, in this case microparticles, right? These are neodymium iron boron ferromagnetic particles, and we can play on how we can arrange these particles, right? And we can design, rather than generate weird magnetic fields that have complex shapes, right? What we're designing is complex materials that can respond in complex ways to very simple magnetic fields, right? And what we can do, as you can see here, right, controlling the arrangement and the polarization of these particles, we can achieve precisely that, right? And maybe we can have another volunteer. I think, yeah, you were from earlier. So what we're going to have in here, yeah, maybe you can come. Yeah, perfect. So do you want to explain, Zane, or yeah, okay, maybe I'll. What's your name?
My name's Sarah.
Sarah. Nice to meet you, Sarah. Please go ahead.
Hi, sir. As you can see, we're here powering it with a voltage with 18 volts. And here we have a control box. If I switch to one of these, we're controlling it to a direction. And here you can see there's a knob. Now we are closing it.
Yeah.
Oh, so here we have a knob. If you can turn it clockwise, you are giving
I think before doing that, maybe you can explain why there's two of these strips.
Oh, sure. So here we have two magnetic strips. We are activate one of these with a horizontal magnetization. Another one, we didn't activate them. So once we are giving it a magnetic field, we are expecting one of them are moving. So if you can turn these clockwise to give it an impulse, we should be able to see one movement. And if you can increase it more, you should be seeing more of this deformation. You can like turn it up or turn it down so that we can see the direction. The other thing we can do is that we can change the direction. If we turn it in this way, if you can do this turning knob again, we can see it's bending in another direction. That's because we are using a negative magnetic field. Thank you.
Awesome. Yeah, thank you. Thank you. Maybe you want to stick for a second because we have something else coming on as well? Yeah?
Okay.
Yeah, thank you. So same working mechanism as a compass, right? So we can achieve in here like this bending of this cantilever by just giving a very silly, simple, homogeneous field, right? But rather than playing with the field, we're playing with the material, so you can respond very differently with this, right? And we can do all kinds of stuff with this. If we are, if instead of this, we're using some other, what is this thing here? We can program the magnetization internally of these materials to use it for many different functions in robotics, as we're going to see right now.
So we're seeing the gripper.
Yeah.
So here I have.
Can you bring the microphone closer?
Oh, sure. So here I have this magnetic gripper, where now it's not activated, but we are programmed it with the magnetization. So once we apply a magnetic field, we should be able to see the deformation. Can you help me to to turn up the field? So as we increase the magnetic field, it should bending down. And can you help me close it by changing the switch? Yeah. And now, if we put a object on the surface, and can you help me turning the switch to that that's the other position.
Scared of the duck.
Yeah. Turn to the number 2 switch. Yes, this one. So here we should be able to lift it. Oh. That's bad adhesive. We are using this force to grip. Thank you. Yes, you can do that. So now we are not able to have that force anymore.
Great. Thank you, Sarah. Thank you very much. Awesome. Thanks. Great. Awesome. Thank you, Zane. So we can use this as a gripper, right? And this is a silly example, right? But we can use this to manipulate objects at very small scales, right? And the beauty of this is that we don't require sensors to control the force, and because this material is soft and compliant, it can adapt to complex geometry. Like you can see in here how when these grippers come in contact with this block M, they can deform and adapt to the surface, right? So you cannot give too much force to break these objects, right? So you can see there like this thing. So you can get very conformal gripping to complex objects, which is very important for us, if you remember, unstructured environments, like things for farming, groceries, cherry tomatoes, fruit, all kinds of food that they're very different from one from another, right? So these type of actuators, they're very precise, but also they're very compliant, so they can be used for many different applications in unstructured environments. So, but this is by having more of a simple, I shouldn't say simple, but a kind of a one-mode deformation. If you remember, we're talking about inchworms, right? Which, how many of you still have the inchworm? One only, okay. 2, okay. So if you remember, we're doing like that movement, right? We can do like that by having a bit of a more complex magnetization programming, right? And maybe, Zane, maybe you can show the example of the inchworm in here. Don't worry, I can talk because you need both hands, I think, for this. So in here, this has a sine wave, a magnetization. So what happens is when you give the magnetic field in here, you're creating the bending. Oh, I think, yeah, you're pointing the other way. You can get like this inchworm motion, right? More or less. Awesome. Thank you, Zane. So we can see this is quite difficult to do it by hand, right? But what we're doing in our lab is, developing the materials, but also the control mechanisms that go with it, right? We can see here on the screen, right? Over here, right? You can see how by controlling not only the intensity, but how you cycle between magnetic fields, you can really control the gait of these micromotors, right? Microrobots, not only for walking, but also for swimming. Thank you. Awesome. Thanks. To enable different biomimetic modes of locomotion, which is using the same modes as we see in the inchworm. And we have one last case to show in the 10 minutes that we have left. This one we don't have a demonstration because this has to do with very small organisms, which are bacteria, right? So we're trying to explore the space at the very, very, very small scales. So one of the challenges of really using these microrobots at small scales is that the ways on how animals swim are very, very different. And I lied. I promised 2 equations. This is 3. But this is very simple. This is called Reynolds number, which tells you what kind of flow you have depending on many conditions, right? As you can imagine, swimming through a fluid with low viscosity, right? Swimming through water is much easier than swimming through honey, right? So, because it's more sticky, right? And you have more friction with honey. The problem is that these effects don't only depend on viscosity, but also depend on the length scale. So you can see in here how different animals, right, operate at very different Reynolds numbers, right? And what you have here is you have different modes of flow versus laminar flow and turbulent flow. We have different drag and different resistance. But just to give you an idea on how difficult it is for bacteria or like small microorganisms to swim in liquid media, bacteria swimming in water has a Reynolds numbers of 10 to the minus 5, which is somewhat similar to a fish like sardine swimming through peanut butter, right? So very, very, very viscous, right? But nature is very smart, right? And came up with very cool ways to swim in these complex fluids, right? You can see here how bacteria has these little hairs, right, called flagella. Then what they do is they have this motor that they can rotate it, right? And they beat it like this. Oh, the video stopped playing. Okay, maybe I'll go back yeah. So they rotate like this, and they use this thing to propel through viscous fluids, right? And you can see this like real bacteria that has been tagged with some fluorophores, so we can actually image this. And this is across many different types of microorganisms. So it's a very common locomotion strategy at the micro scale, right? Okay, so how can we adapt this thing to synthetic robots, right? So what we can do is we design and 3D printed these little corkscrew helical robots that have a similar shape than this flagella, right? So thankfully, 3D printing and some other fabrication technologies are really helping a lot to folks like us that really want to fabricate complex structures at small scales. But what is cool about this is that what we did is we incorporated magnetic particles, and using the same working mechanism as the compass, we can rotate these helical microrobots and literally drill through the fluid. Right? So you can see in here how we have this little guy that is swimming across this liquid, and you can see in here that is going sideways. Depending, there's some other effects in there. You have some friction, but basically the shape of this robot enables the locomotion. Right? And what's cool about this is also we can functionalize it with some drugs. In this case, we use some doxorubicin, which is an anti-cancer drug, for controlled drug delivery, right? So the dream for these medical microrobots is can we use them to deliver drugs at very specific sites of the body, so you can reduce the dosage, increase the efficiency, and get rid of some side effects for cancer therapy, for example. But there's, of course, it's easier said than done. There's many challenges ahead, right? And one of the big problems, and this is kind of what we're very interested in the lab, is how you can consider the biological environment in the design of this robot, right? Because one of the big problems is the body will fight these things, right? The immune system will fight anything that detects as a foreign threat, right? For example, you see here a white blood cell chasing a bacteria and eating it, right? And this is, no matter how fancy or cool and sophisticated your microrobot is, if your immune system is going to clear it out right away, right? And this is one of the problems also with most drug delivery technologies, right? That immune clearance and low systemic circulation is a big challenge that reduces the efficiency of these treatments a lot. But material science comes to the rescue, right? Or that's what we're trying to do, at least. We have developed some materials that have these stealth properties that remain undetected by the immune system. These are replicating the surface chemistry that you see in other cells. And you can see here comparing, these are stealth microrobots. These were co-cultured with macrophages of the immune system that typically chase these threads and foreign bodies in the body, and they eat them up. You can see how in the common biocompatible materials, this is from a material that's kind of like the standard, it's called PEG for polyethylene glycol. You can see how these immune cells are starting to eat it, right? Well, this one with our stealth materials, not quite, right? They're just chilling next to it. So I wanted to show you, just to wrap things up, a video of what happens when we introduce these microrobots with cells of the immune system. So you'll see here on the left, this is the gold standard for biocompatible materials today, and on the right is our stealth materials. You can see on the left how as soon as the macrophages come in contact with this robot, they eat it up. They're like, hey, you're dangerous, I don't like you. And they capture it. But on the right, you'll see how these cells, the microrobots are being inspected, so they detect there's something in there, but they're not triggered, they're not detected as a threat here, right? So that's all because of the surface chemistry of these microrobots, right? That they are presenting a surface that mimics the cell membrane, right? So you can see like this guy here, for example, they're being tested and explored by many different cells, and you can see that there's no phagocytosis. They don't eat it up and clear it, right? So we're very excited about the new opportunities that chemistry and understanding how these physical interactions between the microrobots and cells and other important parts of biology, how that can unlock the next step for bringing these medical microrobots to reality. And with this, I think these are our 3 cases that I wanted to show today. The inchworm, right? This surface tension-driven microrobot, and this bacteria-inspired microrobots. So just wanted to bring back up this slide from early on in the talk, right? I think this is a field very ripe for opportunities, not only from traditional robotics, but also chemistry, physics, material science, all branches of engineering, especially to bring the new generation of robots, that can both know how to play piano, but also have the physical ability to do it, right? And with this, I would like to thank, first of all, my students that have been great, and it's the best part of the job, right? We have to work with very cool people, both in our lab and outside of our lab. And of course, our funding sources, Rachel mentioned Air Force and the MERSEC, right? But also wanted to say, if you're interested in this, please do not hesitate on reaching out. We'll be very happy to show you our labs and some of the work that we're doing on this. And of course, thank you for coming here. I hope you had at least as much fun as we did. Thank you. So then we have the microphone. So, yeah.
So we're getting set up for questions. You can submit your questions here to this email address if you're online, or even if you're in the room, you can submit them there.
Thank you, Monica. Thank you so much, guys. That was fun.
So I'll start us off with some questions from online.
Please. Do we? Oh, you have the question?
I have the questions. How do you make the shapes, and how do you attach materials like squid protein?
Well, the shapes, it depends, because I've showed here like different examples. Typically, the way we make shapes and we design things is either we use some molding, and we can, cast the materials in these molds, or we can use 3D printing with this polymer. Particularly with the squid, what we have done with this is we take like large sheets of materials, and using laser micromachining, we can define the shapes that we can optimize for swimming. And then we apply this squid protein as a coating. We dissolve it in a fuel solution, and it's quite cool because after it evaporates, a lot of this chemical fuel remains trapped in the protein matrix. So it's a very robust way of making these things.
Thank you. Let's take a question from over here.
Hi.
Do you think this project has given you some insight as to how early life on Earth began to move?
That's a big question. Not so much from these projects, right? I think the proteins that we typically work with, right? They're like very large molecular weight, right? So that's not really our area of expertise, right? We have done a bit of like morphogenesis work on how you can how some animals grow, right? And how by giving some different structures and different amino acid sequence in proteins can grow and develop into different materials, but not so far back as in how life started, right? So it's a very important question, but I don't think I have an answer for that. But thank you.
We'll take a question from this side.
Sure. Great talk. Thank you.
Thank you.
Question about the surface tension propulsion, the squid protein. Just so I can wrap my mind around this and try to figure out how to use it, right? The surface tension propulsion, you're putting the surfactant in. There's some differential there, and that's providing that's the locomotion, yes?
Exactly, yes.
Okay. And the squid protein, this is just a way to put a delay on the whole thing and let it release slowly?
Exactly, yeah. So it's just think of it as a chassis, right? As a delivery mechanism. A problem with a lot of, think a bit of you can think of it like a sponge, right? If you have a sponge that can absorb a lot of material, it's great, but also it releases very fast, right? And that's kind of one of the limitations that we will see with this type of motors, that they're very fast, but they're very short-lived. So with this, you can control the kinetics of diffusion and release.
And so that's a good segue to my last question. Do you have some way to modulate, or is it a drop and go?
Yeah, that's actually, that's Chuchi's project, yeah.
Very good.
Chuchi is working a lot on different ways to control this, right? I think I've shown a little bit on using magnetic fields to control the direction, but of course, right now we don't have brakes. Right now is, pedal to the metal, and let's see what happens, right? But it's very important to have like some reversible mechanisms, so you can, from a control perspective, so you can actually do things with this, right? So we're using some chemical stimuli. We can control the opening and closing of the pores depending on the the chemical environment, so it's great for sensing, to have like some chemotaxis mechanisms. But we're looking, and that's what Chuchi is doing, on some active ways to control this thing. So we're trying to get a switch on this.
Thank you.
Yeah, thanks. Great question. Yeah.
Over here.
So in addition to using the spiral motor to deliver doxorubicin to a targeted area, have you considered it to deliver radiation to a targeted area? Could you have like a radioactive seed that you could implant?
We could, definitely. I think it all depends on how you can incorporate that seed in it, right? I think these polymers that we use for fabrication, we have designed some like blends where we can have one that has these like stealth properties to keep the immune system away, but we can incorporate some anchoring points to attach, anything. We use doxorubicin because it was like a model drug that we're using, but we could attach anything to this thing. But that's good. But we have no experience with radiation, so I would love to learn more about it.
All right. Thank you very much.
Thank you.
Take a question from over here.
Hi, I have a couple of questions about the squid protein, just I think two basic ones really. One is with, you mentioned that it kind of lasts for a while because it's, has the permeability and slow release. I was wondering like how long specifically is that, and I guess would it depend on the amount of the paint that you paint on it? And then my other question is basically once you paint on the squid protein, is it possible to like refill that protein with fuel, or do you have to apply a new set of squid protein?
Either. So this is a very important question, and it's something that we suffer a lot in the lab. The problem of refueling is that you have to fish them out, right? So it's not, depending on the application, it's not that practical, right? So that's why we're trying to extend the lifetime of these motors. But you can either refuel or reapply. It's more practical to reapply another layer because it's shorter processing time, right? So we don't do it that much for refueling, but you can definitely do it. Your first question was about how long it lasts. It depends. The larger it is, right, the more fuel you can have, right? So then it lasts for long. I think a lot of you've seen some examples here. I think Chuchi showed some discs on like 5 millimeters diameter. These are like, I think 50 micron thick. So it's pretty small. These last about a couple hours. So compared to other materials, and we try to benchmark that typically last under a minute. So just to give a bit of a apples to apples comparison. But the key is that dynamic porosity that can really self-regulate the diffusion kinetics.
Yes, sorry, just maybe one more follow-up is just like what does the drop-off in like the speed look like? Like, does it stay pretty constant or? Yeah.
It goes down as the fuel gets released. So we have, and you can modulate this with the structure. These 2 hours is for like the total time. Typically you have like about a half an hour, like very fast motion, and then it starts dying out a little bit. But still is pretty strong compared to other types of these Marangoni motors. But thank you.
Thanks. I think you had a question before, right? Yeah. Okay, let's let one other person, and then we'll come back to you. Do you have a question?
Thank you.
Oh, go ahead. All right, go ahead. He's letting you go.
Do you often think about combining the different, like there were 3 different types of motion that you presented today. Do you combine them often?
Yeah. I think I show an example on these surface tension robots where we use magnetic fields to control the steering, right? So I try to show these 3 cases because the inspiration, right, and the design come from different things. But often we integrate a lot of these things, whether it's from the fabrication approach, whether it is from the control. We've seen how we can use magnetic fields for locomotion, but also for steering on this surface tension, right? So sky's the limit, right? Or at least, a small scale, because these are very, very small, right?
You can come visit his lab.
You're very welcome. Yeah. So these are all these different mechanisms, right, and actuation methods. They're tools that you can use to design your devices. Yeah. Hi.
Question over here.
Thank you so much, Professor Abdon.
Thank you. Very good.
Thank you for the team's wonderful work. I'm inspired. Not bio-inspired, I'm inspired. My question
It works.
Thank you so much. It's wonderful.
Thank you.
And surface tension is two-dimensional.
Yes.
Right? Don't have to be flat.
It does not have to be flat. Yeah.
I forgot a term of one of the ring have one surface. Somebody can tell me. You know the ring? If you have a piece of paper,
Oh yeah.
and you twist it and glue it.
The Mobius strip. We were talking about this.
Thank you.
Rachel, we were talking about this
Yes,
yesterday.
we
Yeah.
were.
There is only one surface.
Yes.
As I said, I'm inspired.
Yeah.
If we can base on this, what your discoveries, your imagination, we can even go to from Mobi ring, right?
Yeah.
We can do quite a lot of things
Yeah.
forever in a microscope, and also maybe we can use three-dimensional. I forgot the term. There's kind of like, the ants can claw all over, can only.
Yeah.
What's that? It's like bottle have. Yeah. Yes. So if we can base on this, the basic simple things, and keep going more than 2D, more than 3D, we can.
Yeah.
So how do you think?
I had this discussion with is one of the a postdocs of Sharon Glotzer from chemical engineering. She does a lot of very cool simulation of active particles and active matter. In theory, it's possible, but for experimentalists like myself, we have to actually make it. And that's where the challenge of these things. Because of this surface tension, we require an air-liquid interface, right? So these things will work on this complex surface, but we need to have a wet surface, right? So that's the challenge. If we can get surface tension to hold to the surface, then we could use the thing. But I think that's where the challenge will be. But there's other ways to use Marangoni flow as well in 3D. Yeah. You can create artificial interfaces, right? You can use like microbubbles to generate that bring the surface with you, right? And you can use it underwater for this. It's a bit more difficult because the net propulsion that you get from this mechanism is not that much, and the drag resistance is much higher. So then you have to keep this in consideration. But it's definitely possible. Yeah. But I like the idea about the these more complex 1D surfaces. Yeah. Thanks.
Over here.
Do you ever think about the less good applications of your research? For instance, from what you've described, it seems like you could make like a COVID-19 stealth micro-robot. So, I mean, do you have to think about that ever?
Can you repeat? Sorry, there?
Do you have to think about the less good or the bad applications of your research? So, from what you described, it seems like you could make a stealth micro-robot delivery for COVID-19 or some other kind of virus.
Yeah.
And is that why the Air Force funds you?
No. No. The Air Force is funding us for new materials for this magnetic actuation, for kind of like the inchworm, right? What we have funding for these like stealth things is for controlling the growth of bacteria, right? So this is designed to keep away, in this case, the immune system. The trick behind that is that these polymers have a very thick hydration layer. So you're kind of shielding those structures against all kinds of junk that you have in there, right? So we're using this. We're doing some work to prevent UTIs for this, right? So things in like urinary catheters, which is a big problem, right? Because if you get a catheter, right, it's very common that you go to the hospital for X. If you have a catheter, then you have to stay longer because it's a gross environment and you get infections, right? So it's a big problem, and some patients, they have to wear a catheter all the time. So we're using the same type of stealth materials to prevent the growth of bacteria in those devices, right? And things for like, what's the name? To avoid the foreign body response and rejection of implants. Yeah. But surprisingly, most of our DoD funding, they're very conscious of this, and the ethical implications of these works, right? So they're very careful on these things. So it's a good point. Yeah, but in my experience, at least, right, these things are, I think you called it bad applications, right? Yeah. So they're still very far away from that, and I think there's way more potential, way more interest, right, on using this for healthcare and for more urgent problems that we have. But thank you.
Here.
So I understand how the magnetic fields can be used for sort of steering in a laboratory type setting. I'm just kind of wondering how practical that is for something like targeting cancer.
Yeah.
Because I assume you sort of take the drug and then it's all over the body and you're like, go here. But how do you do that with a magnetic field?
So there's several ways that you can use, right? There's some already equipment in the hospitals that can be used to guide these microrobots, like MRI scanners, for example. Some of our recent work with Zane was using an MRI scanner for simultaneous imaging and locomotion of these robots. Those were bigger though, but you can use them for in a example like you said, like you have like a systemic drug, you can generate some like magnetic traps to accumulate them in a specific region of the body, right? For having like fine control, like you have a magnet, right? As it's circulating, it's gonna accumulate in this region. For navigating like with single robot precision, that is very challenging today. There's a lot of cool research, not only from our group, but many others, friends and collaborators, how you can avoid not only this biological problem of the immune clearance, but how can you navigate against the bloodstream, against flow, right? At that length scale, blood is granular, right? You have to pass through all the red blood cells, for example, right? So there's ways to do it. We just need somewhat of an integrated imaging and actuation system like that. So things like MRI, things as photoacoustic imaging are very helpful for this.
One follow-up. Once it's in the body, one of the things with current drugs is that they do get cleared from the body over time. If you have one of these as, stealth where the immune system can't sort of clear it, what happens after the treatment? Is it just there for the rest of someone's life, or?
That is a good question. I think we can make this biodegradable, right? Biodegradable, that they can degrade over time, right? We didn't do it for this. We have a proposal under review right now, so hopefully we can get some funding to push this. But the beauty of this is that you can play with the chemistry of the material, right? So a lot of things that we're doing, and some of it as part of the MERSEC, right, is on how we can control reversible cross-linking mechanisms. So through the MERSEC, we're using it for recycling of polymers, but the chemistry is the same. Can we integrate these things into these microrobots so they can degrade in the body, so they not accumulate in some organ, or they don't have to open you up to retrieve it, right? So I think that will be the best case scenario, right? And it can degrade over time as it releases the drug. So we have definitely the tools to do this thing. We just need, money to hire somebody to do it. But thank you, very, very good question. Yeah.
There's another question.
Hello. Thank you. This is so interesting.
Thank
and
you.
You just were talking about how this technology is being used to reduce hospital-acquired infections, catheters, Foley catheters probably in particular.
Yes,
Can
exactly.
you elaborate on that just a little bit more? And what specifically is how specifically is the technology being used?
Yeah. So this is it's a very similar polymer that we use for the stealth microrobots, but in this case we apply it as a coating. So the problem is that catheters, they're designed to be very inert, so it's difficult to stick things to it. So we developed a coating using some catechol dopamine, which is like the adhesion mechanism that mussels use, so they can attach underwater to attach to the catheter, and then we grow this stealth coating in there. So the main difference with current technology is because there are some antimicrobial catheters already, commercially available, right? Typically they have things like they have some galvanic effect, or they have some like silver antimicrobial coatings. And what happens, they release silver ions that kill the bacteria, right? So what happens is that these work very well, but the more bacteria you kill, you're making, you have then a layer of dead bacteria, then making a very nice cushion for other bacteria to grow on top of it, right? So over time, they work very well at short times, but over time the effect gets a bit lost. The main difference with our mechanism is that we don't kill the bacteria, we just don't let it attach. So think of like a water slide, like they just go through and they can attach in there. Yeah, thank you. Thanks.
Okay, we have a couple more questions online. What kind of learning algorithms help learn how to change magnetic fields for inchworm, for example?
Yeah, that is a very good question. And I think we saw an example in here how Zane is great, but to having some effective locomotion in this is difficult, right? Because you don't have that same level of control, especially with permanent magnets, right? So to optimize the gate for different functions of this, right, you need to screen a lot of different parameters, right? So what we did is, and this is some part that we did with Sinan Demir. He was a postdoc in Germany that he was the lead on the learning part and on the controls part on this, where we used transfer learning to optimize the gate, controlling the amplitude, the frequency, the different orientation of these fields for different functions, right? So then it was a fun project because our contribution was more on the material side, and we get to torture these materials and throw obstacles at them and see how these learning methods were helping optimize for all these different environments. But yeah.
Okay, another question is, could you actually use, say, bacteria as a robot?
I'm sorry?
Could you actually use, say, bacteria as a robot?
Yes, 100%. This is a field of microrobotics that's called biohybrids, right? Basically, you put the organisms to work, right? Typically, one of the most common approaches for this is you use some of these magnetic particles as a backpack, right? So then you can use this magnetic backpack to guide the bacteria and use their own work to propel them. There's some issues with this in terms of safety, right? Because this can be a very fast way to get sepsis, to get an injection of bacteria, right? But there's some new applications on using these bacteria to recruit some immune cells, for example, in very localized areas. Another example that is quite important and growing a lot is on using not only bacteria, but other type of microorganisms with flagella, which is spermatozoa. Can you improve the motility, and can you have some control over the function of sperm for IVF applications, for example, right? So this is an area where you know, you have a direct impact on a very specific application that is growing a lot. But yeah.
And then the last question that hasn't been already asked is, can or do you put sensors on the micro robots for motion or temperature?
We don't. That is good because in some things we need, in some things we don't, right? In our case, what we're trying to do is we try to avoid putting sensors in there, and we're using the material itself as a sensor, right? For example, these surface tension micromotors, you can use pH, temperature to regulate the porosity, right? How these pores can open and close, and how fast or slow you can release this fuel, right? So it's like a self-regulation mechanism, and you have the robot like itself sensing the environment and adapting their speed and locomotion to those chemical changes around it, right? For other things, maybe it depends on the application, right?
Okay.
But yeah.
Okay, thank you.
Thank you.
Before we close, I want to make one more announcement. Tim is sitting here with a bunch of glasses for the eclipse on Monday. If you don't already have your eclipse glasses, Tim is right here. You can. He's very eager to hand those out. And I hope to see all of you on Thursday at the public lecture, and in 2 weeks on Saturday back here, same time, same place. And let's thank
you.
Abdon again.
And thank you.